Meyers.
Thank you very much. How many people were here for Venkat's talk earlier today? Was that a great talk or what? And one of the things we're here for is to learn. So I said, I need to learn from that unbelievably good presentation, but I didn't have a lot of time to really change things, so I took 2 courses of action. The first one was, I took my shoes off, because I figured that was probably key to the whole thing. And now I'm thinking it's probably trickier to walk around in stocking feet on a slick surface than I thought it was. And the second thing is, I made a note to myself, all it says is, get wife. I already have one, but nowhere did it say wife : unique, so I figure I'm probably in good shape. My original idea behind this talk was to choose a bunch of features in C++11, in C++14 that were particularly attractive to people working on embedded systems. But when I sat down and took a look at the list of features that are in the languages, I realized that this is just not practical. So this is a subset of the new features in C++11. There's a fair number of them there. And the thing is, almost everything on this list is just as useful for embedded programmers as it would be for non-embedded programmers. If I look at it more closely, there's a few things that I might call out as being especially attractive for embedded developers. One of them would be alignment control. That's something which embedded people often care about. Another one would be Const exper, which is a way of shifting computation from runtime to compile time. A third would be the standard array class. It's part of the library. It's effectively a built-in array that they've put an STL interface on top of. Has the advantage for embedded developers, it doesn't require any dynamic heap allocation, which is often of interest to embedded developers. Another one is greater control over how we specify the underlying storage for enumerants and for enumerated values. And the final one would be standard function. Standard function is another part of the standard library. It is a generalization of a function pointer. And in the same way that function pointers can point to functions, standard function objects can point to anything that is callable like a function. This can be especially useful for people in the embedded domain because they can use it for things like callback functions, interrupt handlers, stuff of that nature. So that's just C++11, and the talk also covers C++14. If we take a look at the features in C++14, it's not as long a list, but there's still a fair number of features here. If I take a look here, I would probably point out that const exper functions have now been extended, and then there's binary literals, which means that finally, after 35 or 40 years between C and C++, we can express the fact that ones and zeros are in our programs, rather than having to convert them. Yes, I know, it's quite exciting. No longer do we have to take out a calculator and convert it to hex, and then we have to worry about whether the calculator works. It's just a complete mess. So we have binary literals now, which is kind of nice. If you put both of those feature sets together, this is a subset of the new features in C++11 and in C++14. I have 75 minutes. It is not possible to even give a superficial overview of all of these features. And like I said, they're not all aimed at developers of embedded systems, but they're useful for developers of embedded systems. So what I finally decided was it's not going to be practical to talk about everything which could be of interest to developers of embedded systems. So instead, what I decided to do for the agenda was to pick a small number of topics and go into them in more depth to try to give you a better appreciation for why I think they are important. And the ones I'm going to talk about, I'm going to talk about auto, interestingly enough, which certainly was never designed for embedded developers, but it is so useful in general, and I think it will be just as useful for embedded developers, and I think everybody needs to have a better understanding of why auto is as important as it is. So that'll be the first thing I talk about. I also want to talk about const exper, because that is something which will definitely be of interest to a lot of people in embedded systems, although frankly, I think it will be of interest to people who are working on non-embedded systems as well. Those two topics we will definitely cover. Whether we cover a third topic depends on how much time we have available. So the third thing that's on the list is enhanced enums, which is also from C++11. Now, another one that is very interesting is alignment. I'm not going to talk at all about alignment, but Bartok's talk later on this afternoon will be talking about threading do's and don'ts, and in that talk, he will be talking about alignment control. So you'll have a chance later on today to get an example of how alignment can make a difference. And then the last thing I will remark on is, as we are working our way through these examples, you're going to see that there's a whole lot of other C++11 and C++14 features that we'll see along the way. So during the course of the presentation, you'll see a lot of other things in C++11 and C++14. Because I'm going to be showing a number of features in C++11 especially, and some in C++14, and I'm not going to be specifically talking about them, what I normally do is I tell people that if you see something on the slides and you don't know what it is, then what I encourage you to do is either ask a question or look directly at me and try to look as confused as you possibly can. The latter does not work terribly well in a room this size, especially when I've got lights in my face here. So this is my suggestion. If you see something and you don't understand what it is and you would like to, then please do ask a question. And if you don't want to do that, instead try to make a noise like you were in some kind of physical distress. And I will then take that as a sign that either we need to call paramedics or you have a question. So that's going to be the basic plan. All right, first topic I want to talk about is auto. What I want to do is talk about why I think auto is a useful feature and what it brings to bear. The natural question people say is, well, all right, if I have an expression that will yield a widget, I could just say widget W, or I can say auto W. They both do the same thing. Auto is completely statically type checked. So the question is, why would you want to use auto? So let me start with the least important reason first. So the least important reason is mandatory initialization. So if I say something like int sum, well, this is a possibly uninitialized value. Would someone like to summarize for me the conditions under which sum is not uninitialized? What about static? Okay, the official rule is anything with static storage duration is initialized to 0 in production runs, not just in debug runs, by the way. But that leads to the question, well, okay, what exactly has static storage duration? Okay, you all get credit for, yes, if it's declared static, it has static storage duration. What else has static storage duration? Globals have static storage duration, not that you'd use them. What else has static storage duration? Things in unnamed namespaces. So, or I think it's unnamed names. There's one other thing besides globals. At any rate, so if I say auto sum, this won't compile. That's good. If I say auto sum get 0, this will compile. So the first tiny little thing is you can't forget to initialize something which was declared with auto because it has to have an initializing expression. How many people have ever had a debugging session which was built around failing to initialize a variable? Gall darn it, some hands are going up. So if you use auto, you will never have to worry about that particular problem ever again. That is the least important reason to use auto, but it is a reason. What catches most people's attention at first is just how much typing it can save you. So if I have a vector of string iterators, and I want to do something for every one of those string iterators. So this is a C++11 range-based for loop, so I can say for every one of the iterators si in this container, but notice how I have to type string : iterator, or I could just say for auto si. These two statements do exactly the same thing. Saves you some typing. That's kind of nice. Let us suppose I have an algorithm, and my algorithm, of course, takes a begin iterator and an end iterator, and I've decided what I want to do is I want to create a local variable whose value is the same as the first element in the range. And for purposes of keeping things simple, we will assume that there is at least one element in the range. Well, as everybody knows, the type that is pointed to by an iterator is, of course, I guess we'll go over here, is, of course, type name iterator traits of iterator colon colon value type. Just trips right off the tongue. Or you could say auto. So those are your choices. I don't believe this is clearer code than that. I think this is much more obvious. Oh, this points to what star B is. Actually, this is a copy of whatever star B is. But now let's move on to things which are a little bit more interesting. Sometimes when people are programming with actual types, they use what I call type shortcuts. A type shortcut is where you don't actually type the correct type. You type something which is pretty close to it and which works almost all the time. So for example, if I have a vector of int, and I decide I want to keep track of how big it is, so I say, okay, I'm going to create the size variable, which is going to be the size of this vector, and I say, well, it's an unsigned. The problem is it's not an unsigned. The actual type that is returned by the size member function is vector of int colon colon size type. And the only thing you know, that's a type def, and the only thing you know about that is that it's some unsigned type. Most of the time, unsigned will work pretty well, but you can have some interesting problems. For example, on 32-bit Windows, this code will work perfectly fine because unsigned and vector of int colon colon size type are both 32 bits in size. So they are, in fact, the same type. But if you port to a 64-bit platform, for example, 64-bit Windows, unsigned is 32 bits, and vector of int colon colon size type is 64 bits. Which means that you are actually trying to store a 64-bit value into a 32-bit variable. Just out of curiosity, when people are writing their test cases, how many people write test cases that test containers with more than 4 billion elements? Not many. This will only fail when you have a container with more than 4 billion elements. On the other hand, if you had simply said auto sz is v.size, this automatically gets the proper type of this expression, and that's the type of sz, which means you don't have to worry about losing precision this way. So now we're moving a little bit away from simply avoiding too much typing. If I have a map, the keys are strings, the values are integers, then what I might say is, okay, M is such a map, and what I want to do is, for every element in the map, I want to do something. But I don't want to copy every element that is in the map. Instead, I want to actually refer to the specific element that is in the map that I'm iterating over. So what I decide to do is I say, great, I'm going to have P be a reference to a constant pair, because we know that the contents of a map are pair objects. So what we say is, P is a reference to a constant pair from string to int. This code compiles. This code links. This code runs. This code almost certainly does not do what you think it does. And the problem is that even though we have a map where the key is a string, when I say that the map holds a string, the types of the pairs are pairs of const string, which means that the type of every element in this map is not a pair of string and int, it's a pair of const string and int. Which means what you are asking the compiler to do is to take every pair of const string and int and get a reference to it. But the reference is to a totally different type, a reference to a pair of string and int. Now, to human beings, pair of const string and int and pair of string and int are very, very similar. But to compilers, these are completely different types. They have absolutely nothing to do with one another, which means the compiler will try to find a way to convert the type over here, which is a pair of const string and int, to the type that's over here, which is a pair of string and int. And it goes, I know how I can do that. What it will do is, for every pair in the map, it will take the pair, it will create a complete copy of the string and the int. It will thus create a temporary object of type pair of string and int. It will then bind this reference to that temporary object. We will then have a reference to an object that isn't even in the map. At the end of the loop iteration, it will then destroy the temporary object, which means that even though this compiles, links, and runs, and depending on what you're doing, may or may not pass your unit tests, it is not doing anything to the elements in the map. Even something as simple as reading the contents. You don't want to write anything. All you want to do is read things. Under those conditions, you might think, well, that's OK. But it's not necessarily completely OK. For example, this reference P, if you are assuming that it actually refers to an element of the map, you would be able to take for granted that if you took the address of P, that you would get a pointer to an element in the map. If you take the address of P, you will not get a pointer to an element in the map. You will get a pointer to a temporary object, which means that the pointer that you got is going to dangle at the end of the loop iteration. As a result, this code here is an excellent way to write a really, really inefficient loop that leads to dangling pointers. If that's your goal, that's a great loop. But if that's not your goal, if your goal was to actually iterate over every element of the container, then you probably want to say auto instead, because auto will automatically pick up the correct type, and as a result, P will be of the appropriate type, no temporaries will be created, and there will be no dangling pointers. I think that we can safely say at this point, we are not simply talking about minimizing the amount of typing here. These last two examples are specifically focusing on the kinds of errors that people can inadvertently make by accidentally typing types that aren't quite right, but that are close enough to being right for the compiler to be able to force things to work, for small values of work. Any questions on this particular example, by the way? This is important. OK, so the question is, instead of actually typing the type here, could you just do std map : value type? Yes, you could do that if you wanted to. So that would be a way to avoid the problem. Having said that, in my experience, it is not common for people to refer to the value type of a map. But yes, that would work. All right, so the question is, shouldn't there be a warning about this kind of casting? The problem with warnings is they're entirely compiler dependent. And so in this particular case, what you're asking for the compiler to warn you about is the creation of a temporary. I have never seen compilers that will warn about this particular kind of problem. And in fact, if you think about it, for example, if you call a function which takes a const string, and you pass in a string literal with quotes around it, that creates a temporary and it binds it to the reference. And I think people would be really annoyed if they got a warning about a temporary string object being created there. So the first thing is, I believe in this particular context, it is highly unlikely you will get a warning. And the second thing is, even if you did get a warning with one compiler, there was no guarantee you would get a warning with other compilers instead. All right. Something else that's nice about auto, it is the most efficient way to store function objects. So this is a lambda expression in C++11. So what I'm doing is I'm taking a variable x, I'm binding variables a and b, and I return the result of this formula here. Now, a lambda expression creates a callable object, something which acts like a function. If I wish to be able to store that object so I can use it later, maybe because I want to have a list of functions that should be called at some point in the future, or maybe because I want to store it in a data member of a class, I could store it in a standard function object. This is another thing in C++11. It's a generalized function pointer. However, a standard function object, this says this object here points to anything that acts as if it takes an int and returns an int. There is an unlimited number of functions and function objects that match that signature. It's anything that acts like it takes an int and returns an int, which could be individual function pointers, or it could be giant objects which have lots and lots of state that you've put inside them. There is no way for the author of the template standard function to know how large an object it's going to have to store. Not possible to know that. So the implementer of standard function is going to just make some arbitrary decision about the largest object it will be able to store without going to the heap. Generally speaking, it's going to be the size of a pointer. It's not going to be very big, which has the advantage that standard function objects remain small, and it works fine for function pointers, and then for anything bigger than a function pointer, you're going to go to the heap. But from our perspective, what's interesting is that the result of this lambda expression is a closure, and that closure could be on the heap, and it will be on the heap if the amount of storage necessary to store, in this case, A and B, exceeds the amount of storage that is available inside a standard function object, which in general is highly likely. All of which is a careful, long-winded way of saying this probably dynamically allocates memory. On the other hand, if I have exactly the same lambda and I store it inside an auto, then the compiler will say, okay, what is the type that is created from this lambda expression? It knows what the type is, the compiler is compiling it. It'll then figure out how much space is necessary for it, and auto will then become an object of that type, which means that f1b is an object that has exactly as much memory as is needed to store the result of that lambda expression, and it is not on the heap. It is guaranteed to either be global or on the stack, depending on where f1b is. So auto is the most efficient way to store function objects, because it can always set aside exactly the amount of memory that is required. Okay, so the question is, how would we explicitly relate it to have the same effect as auto? And the answer is, you can't. No, it is literally unexpressible, because every lambda expression has its own type. So there is no way to say, what is the type of this? Let me lie to you. So here's the lie. I need to tell you why I'm lying, by the way. Number one, it's convenient. But that's not the main reason. The main reason I'm lying is because I don't think you're old enough to know the truth. So here's the lie. So the lie is, there is no way to find out the type of a lambda expression. And as a result, we wouldn't know what to write over here. You know, you all look strangely more mature than you did about 30 seconds ago. So here's the truth. What you could do in this case is, auto will deduce the type of this lambda expression. If I wanted to know what the actual type of the lambda expression is, now I could do decal type of f1b, because I've already found out what it is. But what your question originally was, is there some way to say, I want to create a lambda and store it in a variable of the type of the lambda, and that there's no way to do. That's why what most people do instead is they use a standard function object, because it's the closest approximation we have to it. But if you want to declare a local variable that is of exactly the same type as a brand new lambda expression, the only way to do it is with auto. There's no other way. All right, so the comment here is that rather than naming the lambda like this, we should just write a function instead and give it a name, in which case we wouldn't have this problem, which is a perfectly legitimate thing to say, except that it turns out, number one, by that line of reasoning, there'd be no reason to add lambda expressions to the language at all, because everything can be expressed as a function. But more importantly, it's actually more efficient to use this lambda than to use a regular function. And the reason for that is because compilers are more able to inline function calls of lambdas than they are able to inline function calls across function pointers. So as an example, if you were to take a lambda like this and pass it to an STL algorithm, you would be much more likely to get inline code calling through the lambda than if you took exactly the same thing, put it into a function, and passed the function pointer. Okay? And I want to point out that the fact that auto is more efficient at storing function objects is not something that is limited to lambdas. So how many people are familiar with standard bind? How many people are familiar with standard bind? I feel so sorry for you. I want to personally apologize. I didn't have anything to do with it, but I just feel badly about it. So those of you who do not know anything about standard bind, yes, good for you, excellent. But for those of you who, poor souls, who do know about standard bind, and I really do feel badly for you, if you create a bind object and you store it in a standard function, again, this could be on the heap. If you do the same thing with a bind object and store it in an auto, it's not going to be on the heap. It's exactly the same story as for lambdas. So the point is that it's not just that auto is better for storing lambdas, it's better for storing any kind of function object. And the reason that I mentioned standard bind is because that's a fairly common thing for some people to have used. So there are sometimes people who are concerned that by using auto, the resulting code is not going to be as clear because we don't say exactly what the types are in many cases. Personally, I think this is an argument that is overrated and is largely raised by people who have never used auto and have never really given it a chance. However, what I will say is auto is a tool, it is not an obligation. If you think an explicit type would be clearer, if in your professional software engineering judgment you think that writing down a concrete type would be a better way to go, you are more than welcome to do that. But I think it's important to recognize that...
Can I have a question?
Given that your microphone is bigger than mine, I'm going to say yes. However, I have a laser. Yeah, go ahead.
For the previous slide, how to make a vector of such functions, because we don't know the type now. So how to put it?
Okay. Is your question about, you can make a vector of these, you can't make a vector of those.
Okay.
Because if I did, this is going to be a unique type for, well, bind is a little bit different. In general, if you want to have a container of functions, all of which have a compatible type, that would be a motivation for using a standard function object. That is one of the things that standard function objects do well that auto does not do. So I'm not arguing that standard function should never be used. What I am arguing is if you have a choice between using standard function or using auto, both of them would be acceptable. Then I would argue you should use auto.
Okay, but can I assign this to a vector of a standard function?
All right, so your question, I assume, is if I took f2b, could I then assign it into a vector of standard function? And the answer is yes.
Okay, thank you.
Mm-hmm. Okay. Practically speaking, many C++ software developers these days are using integrated development environments which keep track of the static types of what's in your program because they're actually parsing it as you're writing it. Visual Studio is the one that is most commonly used, but Eclipse does this to some degree as well, which means even if you use auto, many developers are going to be able to hover something like their cursor over a variable and find out what its type is, even if they used auto to declare it. So things are not quite as opaque as you might fear. And the other thing is, when it comes to deducing types in a statically typed language, C++ is pretty late to the party. There's a lot of other languages which have done this for many years, and people who have experience in those other programming languages have discovered it is perfectly reasonable to write large-scale production quality systems using implicit type deduction, and it works just fine. So C++ is not blazing new trails here. Having said that, at this point, any questions about auto? Yeah, go ahead.
There are many talks about why we should use auto.
Mm-hmm.
Could you tell us when we shouldn't? Are there any situations where we should? Maybe beside this step function because it's type erasure.
Okay, so the question essentially is, there's lots and lots of information saying when to use auto, under what conditions would you perhaps not want to use auto. So the first thing I would say, in C++ 14, auto, in addition to being usable for declaring objects, can also be used for declaring the return value of functions. I think that in some cases, this actually makes the function easier to understand, and I hope to give an example by the end of the talk. But in other cases, I think that having an auto-derived function return type could potentially lead to confusion, so I would be cautious about that. The two places where auto tends to run into trouble are, number one, with braced initializers. So if you say auto x equals brace 10, 20, 30, it doesn't, actually if you say auto x equals equals 10, you end up declaring an initializer list rather than an integer, which surprises most people. So that's one place where I would certainly not use auto under those conditions. The other thing is for classes that return what are known as proxy types. And that is where you have a class, or actually an interface, usually a function interface, that pretends to return one thing but actually returns something else. And perhaps the best known example is vector of bool. If you index into a vector of bool, you get back a reference not to an individual bit because it can't reference individual bits. You get reference to what is known as a vector : reference. And the same thing happens in bit set. So under those conditions, you have to be careful using auto because auto will deduce the actual type being returned as opposed to the conceptual type that is being returned instead. Having said that, my personal preference is under those conditions, the real problem is that auto is deducing a type other than what you want it to deduce. So my advice under those conditions is to actually take the result of your expression and cast it to the type you want auto to deduce. I'd still use auto under those conditions, which has the advantage that you still can't forget to initialize it, and it's consistent with my general advice to use auto for declaring objects rather than hard coding types. Okay? One more question? All right. So the comment essentially is, because auto is deducing the type of the initializing expression, the type of the variable that you are creating is always going to be the type of the initializing expression. However, if you find yourself in a situation where you don't want the type of the initializing expression, and your example had to do with going from unique pointers to derived to unique pointer to base, where you actually want to initialize an object of one type with an expression of a different type, you have two choices under those conditions. What you can do is you can hard code the type that you wish to use. But the other thing you can do is follow the advice I just gave to the other gentleman, which is to take the result of the initializing expression and cast it to be what you want auto to deduce. All right, so the comment is that there are a larger variety of conversions which will be permitted if you do the cast result as opposed to, see, it's difficult to compare it as opposed to using a hard-coded type. That's a valid point. I will say it's a valid point. I'm not sure the extent of the utility of that particular technique, but it is a valid point. You are correct. Any other questions about auto? Mm-hmm.
I don't know, do you have any comments to simplify the debugging? My first thought that we make it more complex to debug, find the specific type. I have only binary.
Okay, I understood it until you went to the last part about only having binary. Are you saying you're not going to have source code? Okay, the question is actually about the effect of auto on debuggability of code where you only have object code. Do you have symbols in the object code? Yes. Not that it does any good, there's no types in there anyway. I would not expect it to be an issue either way. If you don't have source code either way, then you don't know how it was declared. All you've got is the name of the thing. The symbols presumably don't have the information about what its type is. If there's information in the symbolic debugging information, it should have exactly the same information if it was declared with auto. All auto means is deduce this type during compilation. The type of that object is completely specified during compilation. So if the debugging symbol information is including type information, it will be written in there if it's declared with auto.
I will have just more information about each auto type deduced. Because you said that each deduced type might have completely different type for lambda.
In the particular case for lambdas, every lambda has a different type. And that's true whether you use auto or don't use auto. The lambda expression itself has different types. Now, if you only want to have one type to store them in, because you want to store them in a container or something like that, then using auto or not using auto, you're still going to have to probably end up using a standard function object, because the container will be of the type of a standard function object. So I would not expect there to be any difference in debuggability between those two scenarios. Okay? All right, at this point I want to remark that we're about 35 minutes since you just consumed 500 pizzas. We are sitting in a dark room. We are talking about type deduction using auto. So this is the worst possible time of day. It's right after lunch. I'm droning on about God knows what. So this is what I want you to do. Everybody stand up. If there's enough room, everybody turn around. Those of you watching the live stream, I expect you to get up and turn around in your living rooms. You should be working anyway. Okay, everybody now sit back down. With any luck, that got your blood circulating enough so that we can continue. Next thing I want to talk about is Const exper. In fact, I want to give you some advice. Here's my advice. Use Const exper whenever you can. That's my advice. Const exper. Now, the thing about Const exper is it actually has two completely different meanings. Const exper for objects means that, number one, the object is const, and number two, its value is known during compilation. Const exper, when it is applied to functions, has a different meaning. Const exper, when it's applied to functions, more or less means that if you call it with const exper arguments, it will give you a const exper result. That's a lie, but you are not ready to handle the truth yet. We will talk about the truth when the time arises. I want to start with const exper objects. Const exper objects, they have to be initialized with a value, and that value has to be known during compilation. So if I try to declare a const exper object called array size and I didn't give it an initializer, this won't compile. If I just say sz is of type int, this will compile, but we don't know what its value is. If I tried to say const exper auto array size 1 gets sz, now array size 1, because it's const exper, it has to be initialized, but it has to be initialized with something that has a value known during compilation. sz is not something which has a value that is known during compilation. As a result, this line will not compile. If I say const exper auto array size 2 gets 10, array size 2 is a const object, and its value is known during compilation, so this line will compile, and incidentally, its type will be deduced to be int. The nice thing about const exper objects is that they are usable in contexts that require that we have a value that is known during compilation. One of those contexts, for example, would be standard array, a new type in C++11 that I already mentioned. The size of the array must be known during compilation. So if I tried to say I have an array of int of size sz, this will not compile because sz is not known during compilation. If I try to say I have an array of int of size array size 2, well, array size 2 is const exper. As a result, this line compiles no trouble. And const exper objects are in fact const. They cannot be modified. So if I try to set array size 2 to 100 later on, that will not compile. Yes? Yeah.
You mentioned that when I use outer and initialize with number, it would int, but initializer list.
All right, so the question is about this initialization here. What I actually said was, if you initialize something using braced initialization, it's using the curly braces. So if I used curly braces, then you're right, I'd get an initializer list. However, because I don't wish to go down that rat hole, I'm using equals and there's no braces here. But if I used braces here, then the type of array size 2 would be an initializer list, in which case this line here would not compile. Okay? Does that help? It's even true. Most of the stuff I say is true. My first wife doesn't think so, but most of the stuff I say is true. I'm really glad I attended that talk. All right. Const objects. I'm not talking about const exper. Const objects, they have to be initialized, they could be initialized at runtime. So for example, I could say, I've got this variable sz, and then I could say later on, const auto array size 3 is sz. Now, this line will compile without any trouble at all. This just says, array size 3 is a const object. It's got the same type as sz. Its value is not known until runtime. But once its value is established, it can't be modified. That's what const says. Once its value is established, it can't be modified. But if I tried to create an array object of size array size 3, this will not compile, because array size 3, although it's const, is not const exper. So the thing is that all const exper objects are const, but not all const objects are const exper. If you can declare something const exper, it is usable in a wider range of contexts than it would be if it's only declared const. So when you can declare something const exper, you should, simply because it makes it usable in greater number of contexts. Yeah? So the question is, what is the difference between const exper and define? Define is part of the preprocessor and is not part of the language. And so define, for example, like if I define something, it'll have a type and it gets propagated. I can't take the address of a define. I can take the address of a const exper object because it's an actual object. A pound define is just doing textual substitution, whereas a const exper object, I can store it in a container. I can take its address. I can get references to it. Okay? So the question is, what is the difference between static const and const exper? You can have, I'm trying to remember if you can have, I believe you can have const exper data members, but if you had a static const data member, you'd only have one copy for the entire class as opposed to one for each object. Okay? Thought you had me, didn't you? All right. All right. Okay, bottom line on const exper objects is if you need a compile time value, the tool you want to reach for is const exper, not const. And as I mentioned, if you can use const exper, you really want to use it because it makes things viable in a wider variety of contexts. But the really cool thing, to be honest, is const exper functions. Const exper functions are really different from const member functions. So if you think about const member functions, I want you to forget about const member functions because const exper is really quite different. Const exper, first thing, it's not limited to member functions, which should tell you right away it's not like a const member function. Second thing is, conceptually, a const exper member function executes during compilation. Try not to think about what this means for your compiler writers. Const exper functions conceptually execute during compilation. If you call a const exper function and you pass it arguments known during compilation, and the result of that const exper function must be produced during compilation, then it will be produced during compilation. However, Let's suppose you call a const exper function where the arguments are const exper, but the result is not used in a const exper context. In other words, it isn't used for something like specifying a template parameter value or specifying the size of an array. Under those conditions, theoretically, compilers are not required to execute that function during compilation, and they could defer it until runtime. I have no idea why any compiler vendor would do that. But technically, it's worth knowing that's the way that the rules are written. And if I have a const exper function and I pass it at least one argument whose value is not known during compilation, the const exper function will compile and it will be executed at runtime, which means const exper functions are not guaranteed to execute during compilation, and this is a feature. The reason it's a feature is because it means if I write a function to perform some functionality that could occur on compile time values, but might occur on non-compile time values. I will show you an example shortly. It would be silly to have to write two completely different functions, one to execute at runtime, one to execute during compilation. Why would you have? That would violate the dry principle. So you write one function, you declare it const exper, which says if the arguments are available during compilation and the result is needed during compilation, you must compute it during compilation. Otherwise, the compiler is free to perform the computation at runtime. Yeah? Okay, so the question is the same true for cross-compilers? The language standard does not have anything special about cross-compilers. This is the language specification. So to answer your question, it must behave exactly as I have described. So if a cross-compiler chooses not to execute the function during compilation, it'll have to generate runtime code for the target. Const exper functions, they might not return results that are const. Const exper functions may not execute during compilation. Const exper functions are not complicated, they just take a little getting used to. So the question essentially is, what is the reason behind the requirement that compilers don't have to execute the functions during compilation unless it's in a context that requires that? I assume that's just to give compiler implementers flexibility. As an example, one could imagine that compile times could be longer if you're executing a lot of const exper functions. So a compiler vendor might decide they want compilation to run more quickly in exchange for runtime being a little slower. I'm not the guy who made the decision, I'm just the messenger. Let us suppose we have the following situation. So what I'm doing is I'm running an experiment for some kind of scientific research. And in my experiment, which probably consists of growing vegetables and torturing them or something like that, I've got 3 possible lighting levels. The lighting level can be high, low, or off. There are 3 possible fan speeds, high, low, and off. There's 3 possible temperature variations, high, medium, and low. In general, let's assume I have n independent 3-valued conditions, which means there's 3 to the n combinations. Let us suppose I want to use a standard array object to store the results of all possible combinations of variables. That means I need to be able to compute 3 to the n during compilation so I can figure out how big this array is going to be. So that's what we're going to do, is we're going to write a function which will calculate 3 to the n during compilation. So I'm going to show you the interface first. So I'm going to call it pow, and Venkat's argument to the contrary, I'm actually going to generalize, and rather than just hard coding in 3, I'm going to believe I will want to be able to generalize. So there's the base, there's the exponent. So here's pow. It's a const exper function. Because it's a const exper function, that just means if this int and this int are known during compilation, then this int, if it's used in a context requiring a compile time value, will be computed during compilation. So the number of conditions is 5, and because I know it during compilation, that's const exper. So I can declare a standard array of int of pow of 3 and numcons results. This will be computed during compilation. Now, I haven't shown you how to write the function yet, but I want to show you how you use the function first. In this particular case, I'm calling pow with the number 3, clearly known during compilation. I'm calling it with numcons, which is const exper, by definition known during compilation. The result of calling pow is being used to specify the size of an array, requires a result available during compilation, which means I know that pow will in fact run during compilation. I can also call pow at runtime. So if I read a base and an exponent from the database, I can now say, okay, great, I have runtime values for base and runtime values for exp. Notice that I can still call pow, it now executes at runtime. This is what I was saying before. I don't have to overload on executes during compilation or executes at runtime. It's determined by the availability of the operands and the requirement that the result be available. Const exper functions are constrained. There are some restrictions on what you can do with them. In particular, the first thing is they can only take and they can only return what are known as literal types. A literal type is essentially a type where the values can be computed during compilation. That sounds more restrictive than it is, as I will shortly demonstrate. And there are some arbitrary implementation restrictions, and they're different for C++11 and for C++14. We'll start with C++11 because those compilers are more commonly available right now. The first thing is, there is a very simple constraint on the implementation of a const exper function. It has one executable statement, which must be a return. And it took C++ programmers about 12 nanoseconds to go, well, that's okay, because I can use ::, instead of an if-else, and I can use recursion to eliminate iteration. So this is how pow can be implemented. So I get a base, I get an exponent. If the exponent is 0, I return 1. Otherwise, base times pow of base and exponent minus 1. So that is a single statement consisting of a return, and it will, in fact, compute base to the exponent during compilation in contexts that require it. For those of you who are functional programmers, you may think, oh, finally, C++ has functional programming. For those of you who are normal, it'd be better if you could go to C++14, because in C++14, the restrictions on const exper functions are significantly relaxed. You can now have multiple statements. You can have local variables as long as they're of a literal type. You can do iteration statements. So this function here, pow, this is valid in C++14. Notice I declare a local variable. Notice that I have a loop here. Notice I'm doing assignments and stuff. I return the result. That will compile. It will yield the right answer. Yeah. I'm sorry? Oh, so okay. So the question is, what is an iteration statement? An iteration statement means a loop. So for loops, do loops, while loops. And in C++14, they are permitted in const exper functions, such as I have right here. They're not permitted in C++11. So in C++11, going back one slide, what you do instead is you tend to invoke the functions recursively. And so there's a general equivalence of iteration and recursion. So the question is there some stack limit? Given that there's a physical amount of memory on your computer and even virtual memory address space is limited, the answer is yes. Every compiler imposes some particular maximum iteration depth for recursion. I think I heard recently that GCC defaults to 512. Where have I heard that number? But apparently it can be increased. But anyway, I mean, practically speaking, compiler vendors, compiler writers have to be able to detect when somebody has infinite recursion going on. So yes, there's going to be a limitation on that. So
last question.
No, there's no more questions right now because I really need to get through a few more slides and we have limited time here because I haven't shown you what's really cool yet. I mean, this is nice. This is semi-cool, but we can do better. Because we can have user-defined types that are of literal types. So, for example, I can have a class point. Now, the point has x and y. It's a two-dimensional point. Notice I have a constructor. The constructor is const exper. This means I can construct point objects whose value is known during compilation if their x and y values are known during compilation. And that means I can also have getters. So here's x value and y value. They're actually getters, which returns the x value and the y value. They're also const exper, because if I have a const exper point, its point values are known during compilation. If its point values are known during compilation, I can get those point values during compilation, which means I can, for example, say, okay, P1 is a const exper point with this set of coordinates. P2 is a const exper point with these coordinates. Conceptually, this constructor runs during compilation. Which means, now that I've got const exper objects of user-defined types, I can write const exper functions that take them. So I can write a function called midpoint that takes a reference to a const point and a reference to a const point. Yes, you can have references in the interfaces to const exper functions. This is a const exper function, and what it does is it'll return the midpoint of 2 points. So it calls the getter, does some math, and this can be determined during compilation. So now I could say, okay, mid is a const exper object that is the midpoint of P1 and P2. It will compute the value of the midpoint of P1 and P2, and that value will be put into mid, and mid is now a const exper point object, which means we can call additional functions with that. This, I think, is very nifty, especially if you're an embedded developer and you want to shift as much work from runtime to compilation as possible. In C++14, one of the really nice things is even the setters can be const exper. So set x is const exper, set y is const exper. The reasoning behind this is, as long as the compiler can trace through the data flow to figure out all of these constant values, you can push it pretty much as far as you would like to be able to. So these are now, I've got the setters, and once I've got the setters, this means I can write a const exper function called reflection, which will return the reflection of a point P with respect to the origin. So here's my const exper function. This is C++14 now. I declare a local point object. Notice that it's not const exper. It's a modifiable point. I then set its x value to the negation of the point's x value, set its y value to the negation of the point's y value, and I return the result. That's all computed during compilation. P1 and P2, they're the same const exper points I had before. Mid is the same const exper point we had before. I have not changed that. And now I can take the reflection of the midpoint and make that a const exper object reflected mid. I think this is cool. Try that with a number pound defined. If we take a look at const exper and we evaluate the pros and the cons, the first thing is, and this is the reason I chose this for this talk on C++11 and C++14 features for embedded developers, it can shift runtime work to compile time, which means potentially you could move objects from RAM to ROM. The other thing that's really nice about const exper is that const exper begets additional const exper. Basically, const exper objects and functions. The more const exper objects and functions you have, the easier it is to write other const exper functions and objects that are dependent on those things. So once you start using const exper, you begin to realize there's an entire const exper ecosystem you can build up in your programs, which was not possible using any of the more traditional approaches that we did in C++98. It was possible to do certain kinds of things in C++98, but they generally involved template metaprogramming, and people would eventually die of exposure. So this is a much nicer way to achieve the same kind of effect. The major disadvantage of const exper in practice, in my opinion, is that it is part of the interface. So if you declare a function const exper, or if you declare an object const exper, you are making promises to the people who will be using that object or the people who will be using that function. And in particular, you're saying for the object, its value will be available during compilation. For the function, you are saying if it's called with arguments known during compilation, it'll return an argument that is known during compilation. That will impose restrictions on your implementation. You're only going to be able to take and return literal types, and although there are many kinds of statements that can be used in C++ 14, you still can't use everything. For example, if you are confused about what's going on and you decide you want to add a debugging statement, like a printf statement to see what's going on, printf is not a compile time function. It's not a const exper function. And suddenly your whole system can stop compiling. So you only want to use const exper if you're willing to commit to it for the interface. But as long as you are comfortable with that constraint, const exper is a great tool. Any additional questions on const exper? Mm-hmm. Okay, I think there's a couple of questions here. So I think one of your questions specifically is about the standard string type. I believe that as of C++ 14, there are 0 const exper constructors for standard string, which means it's not a literal type and you can't use it in context requiring literal types. Furthermore, dynamic memory allocation and deallocation are not among the kinds of things you are permitted to do inside const exper functions. So that's a general limitation. Does that answer your question? Okay, so the comment was that this means that the code would compile fine, but it's not const exper. Remember, you can only call const exper functions with literal types. String is not a literal type, so you can't even pass a string into a const exper function because it can never because it's not a const exper object in the first place. Sorry.
When you ask further questions, sorry to interrupt, Scott. When you ask further questions, would you like to raise your hand so that we can give you a mic?
Okay.
I already have a mic. Here. I have 2 questions.
Is it bigger than my mic? All right, go ahead.
I think so. I have 2 questions. One is that I've noticed that all your const exp functions has no except qualifier, and the question is it necessary?
Okay.
And the second one is that if a member function for class is const exp, does it implicitly mean that it's a const function?
Okay, so question 1 was about my use of no except, and you may have noticed that I have no except sprinkled on most of these const exper member functions. So your question was, is it required? The answer is no, it is not required. And this being C++, it actually is possible to have a throw statement in a const exper function, but that's a much longer discussion. The reason I'm using no except on them is because the existence of no except on functions that will never throw an exception can permit the compiler to generate better code if it executes at runtime. So I've chosen to use no except because the examples that I've given, I believe they should never yield an exception. They're not doing anything that should ever give rise to it. So if for some reason they are called at runtime, I would prefer the compiler to be able to generate the best possible code. So that's why I'm using no except. And then the second question I have forgotten. Can you remember what your second question was?
The second was if a member function is const
Oh,
exp.
thank you, right. Okay, so the second question was, if I have declared a member function const exper, does that imply that the member function is const? The answer in C++ 11 is yes. So, and that is why, in fact, when we go back, and I showed you these setters here, these setters in C++ 11 cannot be declared const exper because they're assigning to x and y would implicitly be const in C++ 11 in a const exper member function. However, they changed the rule for that in C++ 14, and that is why in C++ 14, A const exper member function does not imply that it is const, and as a result, x and y can now be assigned to.
Sorry, gentleman over there in the red
Yeah.
shirt, please.
Yeah, just a short question. Default constructors are const exp or not?
I'm sorry, one more time?
Default constructors, are they const exp or not?
As far as I know, there is no such thing as a function that is automatically generated const exper. So anything generated by the compiler will not be const exper. So the only way to get a default constructor that's const exper would be to manually declare it const exper yourself.
Okay, thanks.
I thought we had a question over there. Could we get the mic there, please?
When you come up here so you can see the room a little bit better.
It is possible to make some compilation assertion. I mean, for example, in the compilation phase, when one value is evaluated below 0, then show compilation failure. So some error. It's possible?
So is your question whether it is possible to, for example, have some kind of an assertion in there which will cause compilation to fail?
Yes, yes.
I'm going to answer yes and tell you that there's a longer story behind that. But the answer is yes. Any other questions?
Sorry, question over there. Would you like to pass the mic, please? Gentleman in the striped shirt, please.
Why does compilators do not assume the const exp? I mean, they can calculate the things. If it's possible, they can generate code in compile time, else they can just ignore it. I mean, you can write, for example, a script that will make everything const exp, then it will run compiler, and then remove all the const exp that shows an error. Why doesn't it assume? I guess with that approach, we'll have const exp like register on inline. The keywords that exist, but they are not used.
Can you say the question again? I didn't follow the whole thing. I'm sorry.
Okay, so let's assume we want to do some compile time optimization, yeah? And I'm writing a script that every single object and every single function I add const exp, yeah?
Okay.
Then I run compilation,
Yes.
and I see the list of errors. I remove all the const exp with those errors,
Okay.
and after that I get the maximum possible const exp in the code, yeah?
Okay.
Why doesn't compilers do that? Why I have to, as a programmer, take care of that?
Okay, I mean, so essentially what you're wondering is why doesn't the compiler just do all of this automatically itself? And the primary reason I think is because const exper is interface. You're making an assertion about something. So if you declare something const exper, the compiler enforces certain constraints. But if you don't declare something const exper, then the compiler assumes that those constraints do not apply. But the thing is, it can't read your mind to determine whether the interface is never, ever supposed to be changed, or whether the interface permits, for example, runtime implementation. So essentially, by putting in const exper, you are asking the compiler to enforce an additional set of constraints. And to imagine a particular example, let's suppose I have a function and I don't declare it const exper. But the compiler determines it could have been declared const exper. And so it certainly treats it as if it were declared const exper. That might allow code to compile elsewhere in the system that should not have been able to compile, because it will call the function as if it's const exper, which is a guarantee that it will never change, but it might be changed in the future. So I'm going to assume, I don't know for sure, but my guess is that the people standardizing the language did not want to have a piece of interface put onto an object or a function without the human being saying that interface should be applied. Does that make sense?
Yes.
Okay.
I think we've got time for just one more question. Gentleman waving over there, please. Over there. Would you like to raise your hand again?
I'm going to go through 2 more slides after this.
All right. Can you overload on const exp? I assume you can calculate square root for example, at compile time, but at runtime you can choose a much better algorithm to do this.
If you want to have different functions for runtime and compile time, you have to name them differently. The thinking behind Const exper functions is that it should be able to run either at runtime or during compilation. If you don't want that behavior, then you're going to have to make sure that you don't overload the function name. Does that answer your question?
Partially.
Okay, more explaining.
It's the last question. Go ahead, give it a shot. What's the other half?
Well, I want my function to be able to be called both at runtime and at compile time.
Okay.
But it could be made much faster at the runtime without using iteration. And as an example, I would put square root, where you can.
As far as I know, there is no way to detect during execution of the function to find out whether it's executing during compilation or at runtime. I know that people have been looking into that, so unless somebody has found a clever way to determine that, it's not possible. The language itself doesn't give you a straightforward way to ask that question. Whether somebody has figured out some clever way to make that determination, which means you could branch to decide what you wanted to do, I don't know.
Okay, thank you.
Okay?
Okay, I doubt that we've got time for any more questions.
No,
and I know that,
yeah.
so please do
I just want to
continue.
point out that the material that I brought, it covers one more topic, which is enhanced enums. The PDF will be made available for people who attended the conference. We're not going to have time to go through that, so I just want to let you know that it's here. And I also want to point out that if you're looking for information on using C++11 and C++14 in embedded systems, there's a couple places to go. So there's a set of notes that Rainer Grimm did last year at Meeting C++, which gives overviews of all these features. William Wong, he wrote an article earlier this year that covers all these features. So if you are interested in the general topic of using C++11, C++14 in embedded systems, there are other places to go for it. I need to plug my book because my publisher really likes it when I do. It is a work of pure genius. So. This is the nicest audience I have ever had in my entire life. So. You guys are, even nicer than my next wife, so. Okay, information on C++11, information on C++14, and then there's also some references for other things we talked about, like auto, Const exper, and enhanced enums. So, thank you very much. Thank you.